Tigadan 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 pam pam tigadan 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 pam pam tigadan 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 pam pam tigadan.
All right, our next presentation comes from Heiko Schick, who's the chief architect at Huawei, where he'll be presenting graph neural networks. Heiko, welcome.
Thank you for allowing me to give you a presentation about the research work we are doing on graph neural network. What I would like to show you today is a bit giving you an introduction in what we're doing with graph neural network, also describing the intention or the aim behind it, and also showing the similarities, but also the research challenges which are coming with graph neural networks compared to convolutional neural network, which you all know. Speaking about convolutional neural network, in the last years, we made really tremendous and significant improvement when it's coming to artificial intelligence, especially also that basically we have now networks which can beat human performance. And here, as one example, there are many, many more examples in the internet. You can see that we are using image classification based on ImageNet. And if you look at the results, typically this kind of benchmark, as you surely might know, takes the top 1 and top 5 guesses. And if we now look at the results and compare it with human beings, which you can see in the upper red line, you can see that since 2 or 3 years, basically neural networks, when it comes to this kind of classification tasks, to detect the top 5 accuracy, basically, or the top 5 elements, in this kind of model already beat the human performance, which are typically having a classification error of 5.1%. So now image recognition is, I think, well known, and a lot of people might already using it in very different applications when it comes to artificial intelligence. So what we basically also saw or realized when we were looking into a new research direction is that graphs typically are everywhere. I mean, pictures are well known, but also graphs are very well established within the IT industry. We are using it for social networks. We are using it for neuro-linguistic programming. We have it in recommender systems. Like when we buy something on the shop, we get some advices what we need to buy in addition to that as well. It's used in high energy physics, for example, for neutrino detection. It's used in the chemistry for drug and material molecules analysis. We have it in 3D, computer graphics, and so on. So graph is basically some way to represent very complex data, and using artificial intelligence to analyze graph would basically open a very wide field of new application scenarios. And that was in principle the interest why we started with graph neural network and started to look into it. Looking simply what a graph is, a graph basically is an ordered pair of nodes and edges, which are mainly defined by the neighborhood. The nodes typically have no real order, and also graphs are sometimes challenging to visualize, especially when they are very big, because also, as you can see in this example, 2 different graphs can be drawn and showed in very different ways. Another reason why we need graph neural network is that typically standard neural networks like GNNs for image processing or RNNs cannot handle graph input very properly. And we are trying to solve this problem by GNNs. So the team are working on different models to see where we have some which models are working better or which models are not so working well. But we clearly realize that analyzing graph with traditional models will not work. In addition to that, also graph neural network typically can do propagation guided by graph structures much better as traditional neural networks. And this was the encouragement starting for us looking into this research direction. So introducing graph neural networks a bit, and here the pictures are based on a paper from Thomas Kipf and Max Wieling, which was published in 2017. You can see that graph neural networks typically use information about the graph structure to extract feature. And also it uses the extracted feature to assign labels to the nodes, which later on is also used by node classification. So the advantage is that the extracted information it can be used in a non-regular complex structure. And then also, in addition to that, similar like with convolutional neural network, we also can do graph convolution. And as you will see later on, graph convolution is not so much different as the convolution we're doing with convolutional neural networks. And typically it's, as I said, very similar to image convolution. You can multiply features with weights. You can aggregate neighbor features. So it's very similar to what we already known with graph convolution. But looking a bit at the architecture of a convolutional neural network, I'm not sure, to some of you it might already very well known, some of you it might be new topic. We can see that typically a neural network to process images has several convolution layers. And in this case, it's a very simple network, just to show you a bit the convolution layers. And then when we want to analyze, in this case, a 9, which is normally represented as an image. We have red, green, and blue value. We have the numbers, and then this kind of pixel information can be easily represented in a matrix, and then the matrix can be used for kernel convolution, where we very simply just do, simply speaking, matrix multiplication. And this kind of functionality can be implemented very easily and very well in hardware. And then we go over every pixel, use this kind of kernel, and in principle execute a kernel convolution. So now with graphs, it's a bit different. With graph, normally, in order to be able to do convolution, what we need is a so-called adjacency matrix. An adjacency matrix is nothing else as basically describing the graph in a very structured way, where you can see that basically the elements within this matrix are the edges of a graph, and then on the outside we have the nodes, and basically this matrix is used to describe if we have connections or not from one node to the other nodes. And this kind of matrix typically is mostly sparse, which brings us later to some additional challenges when it comes to hardware. Also, this matrix then can be used for the convolution operator, more or less you saw before, and also it can be used to propagate signals within a graph. So the mathematics behind it is actually very similar to what we already know. And comparing natural images with graphs, you can see that typically images is normally a collection of pixels, and the pixels basically the pixels are basically the nodes which hold a feature vector. Typically also pixels are normally dense. So here we're talking about dense linear algebra, and they are normally symmetric. And you can see here, for example, we have a pixel, then we have the weights of the neighbor, and this makes it also very simple to do the convolution. Now, when we're talking about a graph normally is a collection of nodes and edges, and the nodes and the edges in this case hold also the feature vector. As you can see here, we have the nodes, and then all the neighborhood nodes basically hold also the feature vector once it comes to the execution of the neural network. Here, graphs can graphs can feature arbitrary in different domains, and also typically this information is mostly sparse. So while a lot of hardware acceleration is strongly optimized for dense linear algebra, for sparse matrices, we require to have specialized hardware for sparse operations, which also basically means having different challenges towards the memory subsystem and so on. But what do we get when we, for example, have a graph neural network, and what is the output which a graph neural network gives us? So what we can do is we can do node classification. So basically, if we have a citation graph coming from the Cora data set, we can, according to the to all the neighbors, we can classify a node, and we could say this kind of paper belongs to one or the other category as one example. So we can do node classification. So we can classify one node. What we also can do is we can do graph classification. So we can basically take a graph or a subgraph, and we can classify that this belongs more to this group or another group. And last but not least, we can also do link classification. So typically we can classify one link between two nodes or several nodes, and this can be used, for example, also for recommendation systems. And this gives us a very wide range of application scenarios. So when we started, we looked at many research papers where graph neural networks are used, and later on I will show you one example where we had some results recently for physics. And you can see that graph neural networks are used at the moment in chemistry and biology, for drug design and discovery, for medication, mostly also to analyze electrical health records, and to recommend certain medicine treatments, or to recommend certain medications. It's used in cancer treatment, especially when it's about analyzing the patient's genomic data. And it's also used in chemical classification, where you would like to get the idea on what are the chemical behavior of certain molecules. It's used in combinational optimization, mostly also for traffic planning, routing, and network scenario. It's one interesting domain here is also that graph neural networks now showed recently strong success when it's about the design of new processor, when it's the routing and the placement of certain elements. And here it's used from architectural design, logic synthesis, verification, floor planning, placement, routing, and so on. And graph neural networks is also strongly used in computer vision. So like, for example, you can do action recognition. There are really interesting papers where you basically can analyze the movement of a person. And then you basically define this movement, like the connection of a person with his match drawing of a person. You can analyze the movement of the graph, and then you basically can detect what kind of sport or movement the person is doing. So you can detect if the person is doing, for example, judo, or if it's more a gymnastic sport, and so on. But also you can use it to analyze point clouds of 3D LiDAR data. So sometimes you have the situation, like for autonomous driving, that when you have a LiDAR, that some of the points are occluded or not really easily seen because you have a car in front of you, or other people or other objects are basically avoiding that you can see the entire object. But with this 3D graph neural network, you can also analyze the point cloud. You can extend it and can easily detect what kind of object it could be. So you can see there is a very wide application scenarios where graph neural networks can be used as well. But what is the challenge when we execute a graph neural network when it comes to new hardware? So typically a hardware, whatever kind of AI acceleration device for inference and training you're using, has several components. So normally we have kind of a scalar unit on it. We have kind of a vector unit, typically also implementing things like a fully connected layer or ReLU functions and other things. And last but not least, we have a more high intensity computation unit, tensor cores or cube unit, how it is called in our case. And this kind of cube unit are normally optimized for multiply and accumulate operations, but also mostly these units are very strongly optimized for dense linear algebra. And the reason why these units are optimized for dense linear algebra is very, very clear. I mean, if you look at this slide, and you look, for example, in the task to multiply two matrices with each other, you can see that if you do it on a scalar unit, in this case, you would need around 8,192 cycles. And this basically also will end up that for every cycle you would need to do 2 read and 1 write operation, meaning also that the compute density is very low, but the flexibility is very high. In contrary, if you do this on tensor or cube unit, you can do it with a much shorter amount of cycle, but for sure also you will have a stronger back pressure towards the memory subsystem, resulting in very high compute density, but very low flexibility. So we also need to think about where can we fit in sparse linear algebra. Clearly, there are ways, for example, that we can modify a sparse matrix or a matrix for a sparse matrix in a way that we can partition it, that we make it more dense, allowing it maybe to execute it on existing hardware, like in this cube unit. It can be executed in a vector unit, where maybe we have a bit more freedom and we are somewhere in the ballpark, allowing also us to do sparse linear algebra with all the specialized matrix format, or it can be done on a scalar unit with a very low performance. So this is the software aim, what could be done. On the other hand, we can also think about how can we change hardware in a way that we have better prefetching mechanisms or other things, so that sparse matrices, which are typically also resulting in random access towards the memory, are executed in a better way. The reason why we need to think about that is if we look at a neural network, and here, for example, it's a traditional convolutional network with AlexNet, you can see that most of the computational task is executed on the convolution layer, where you can see that most of the parameters that need to be processed and most of the flops which are required are in the orange parts, which are the convolution layer. And then we have some minor functionality, and we have the same in graph neural network, where we have some max polling layers, fully connected layers, which can be easily executed more on vector units. But for this convolution layers, we need to think about how this can be improved. Here, in this case, with AlexNet, again, it's a dense matrix with graphs typically, which are having this very big adjacency matrices. We're having a strong sparsity. And now if we look, for example, at the training of one graph neural network, which we are doing in our laboratory, you can see that the sparse tensor operation consumes 58% of the entire training process, while all the other functionalities are basically in the lower 1-digit range. So to optimize sparse operation is very crucial for graph neural network. And if you can do that very efficiently, you can basically get something new. In this example, we are doing a physics simulation, which is done by one of my colleagues, Tao Wu, and you can see on the left-hand side the ground truth, which is a traditional physics simulation based with executed with computational fluid dynamics and the normal approaches. On the right-hand side, you can see what we can do when we're using a graph neural network. In this case, it's a message passing neural network. And you can see that the prediction is very much the same or very much close to the ground truth on the left-hand side. So now the advantage is you can do this simulation in a much shorter time frame, especially when you have specialized hardware and software for graph neural networks, as you would need if you do the traditional algorithms for computational fluid dynamics. And this is basically one interest of us, why we're looking into graph neural network and why we would like to optimize it to accelerate the execution of scientific simulations, like in this case, this very complex particle simulation. In this case, we are using a water-based simulation, but you can use different materials. You can use sand and other components. You can also use different scenes where you basically have a ramp. You can see in this example, there is a black ramp in different places. So it's very flexible. And that's basically also one of this research direction, which is very much interesting for us. So normally, our opportunities or the research opportunities we see is that to use graph neural networks for complex particle physics, also to think about how existing software stacks or how new hardware approaches can be optimized, so that the already mentioned before sparse linear algebra operation, especially the matrix multiplication and the matrix vector multiplication, can be optimized. Another really challenges where we're looking at the moment is the Cora dataset is very small, so that you can easily execute it on one accelerator. But once you have bigger graphs, you also need to think about how can you distribute the training for this kind of graph, and how do you handle, when you do the distribution training, how do you handle the node graph and link classification? So we also looking into that, and like in all topics when it comes about AI, one challenge we also have is what kind of explainability can you use for graph neural networks? So we're seeing here that the current approaches which are used for convolutional neural network, for example, they show that in theory it could work, but also we see that when it comes to the practical usage, that there are still some levels of improvements required in order to be really usable or sustainable for graph neural networks. So having that said, I hope I was able to give you a bit of an introduction and the motivation why we're doing research in graph neural networks, also give you an idea what could be an application scenario and what are the challenges when it comes to operators for graph neural network, and also show you at least one application in a more detailed way, which is physics simulation, why graph neural network could really bring a strong benefit towards the HPC community. So thank you very much for your question, for your time. And if you have questions, then please feel free to ask me now or contact me at a later time frame.
Thank you, Heiko. I currently don't have any questions in the queue. Hussein, do you have any commentary on your side?
I have a fast question. You know, when I'm talking about neural network, I do always imagine this black box, but this is something maybe we can take it offline because it's a long story. However, what I would like to know is related to the cost. I mean, I know that graph requires a huge amount of data, and managing this data is not an easy process. You know, there's thousands, even millions, and I know that this data should grow at a certain point to be able to provide, you know, good performance. So how are you dealing with this problem, this limitation?
Well, I mean, in our accelerator, to handle the data more profoundly, what we basically implemented also is kind of with this cube unit, kind of a systolic array, where basically the data movement can be optimized. And also we are looking into new memory technologies, which are more performant. And then also when it comes to handle data clearly, especially for sparse linear algebra, as I said, in these matrix operations, there are ways how you can have prefetches, how you can have software hardware co-designed prefetches, for example, in order to handle the data easily. When it's about the management, I think in general, you have the similar challenges as with big image data sets and the others. So these are basically, I think, where we can already benefit from the existing frameworks.
Okay, thank you.
Great. Thank you, Heiko. I currently don't have any other questions. So I'd like to thank you for your presentation and time today.
Thank you.
Tick-a-dum, pam, pam, tick-a-dum, 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 pam, pam, tick-a-dum, 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 pam, pam, tick-a-dum.